My youngest brother has 2 degrees, one in chemistry and one in biology, and he said to me one day, "Why do you make kids balance equations?" And I said, "Because they're on every test in college, and truth of the matter is there's no science to it, it's just accounting." And he said, "Thank you. Thank you for saying that." So here we go. I'm going to teach you how to balance equations anyway, but I don't think balancing equations really teaches you anything about science, but they are on every test, including uh, Chem 1 at South Brunswick High School. So here we go. Balancing equations is supposed to demonstrate the law of conservation of mass, that you're showing that the number of particles and types of particles on the reactant side is equal to that of the product side, so matter is neither being created nor destroyed. And when you do this process, the only thing you're allowed to do is to take the chemical formulas and put molar coefficients in front of them. And this changes the amounts of the particles that you're using so that the overall number of atoms on your reactant and product side winds up being the same. So they say, look, when you're doing this balancing equations exercise, remember that you can only change the coefficients that are in front of the chemical formulas, not the chemical formulas themselves. In other words, suppose I had this reaction. I'm going to take hydrogen and oxygen and molecular hydrogen and oxygen and combine them together to produce water. I've seen students go, hey, I can do that. There's 2 hydrogens on the left, there's 2 hydrogens on the right, there's 2 oxygens, so I'm going to put a 2 right there. Well, the problem is H2O2 is something called hydrogen peroxide, not water. And if you drink water, it's a colorless liquid that refreshes you. If you drink hydrogen peroxide, it's a colorless liquid that kills you. So you can't change the actual formula of the chemical, but what you can do is change the molar coefficients. If I put a 2 out in front of the water molecule, 2 moles of water, now I have 2 oxygen atoms on each side, and all I have to do is say, hey, let's use 2 moles of hydrogen. Now we have 4 hydrogen atoms on both sides. The hydrogens are balanced, the oxygens are balanced, the world is perfect. Okay, so what are the rules then for balancing equations? Again, balancing equations is supposed to show that matter is neither created nor destroyed. You cannot change the subscripts that are in the formulas. So in other words, if you can't create the correct formulas from chapter 7, you're going to have a hard time in this chapter. Coefficients, the molar coefficients can be changed, but you can only put a molar coefficient in front of the formula. You can't put it halfway in between the formula. That would be kind of silly. All right, so what is the technique then for balancing? Look, I tell students, guess, check your guess, keep guessing, but if you need a process, some people prepare an inventory of their reactants and their products atoms, and then what they'll do is they'll make a guess at balancing one of them, and then they'll see what the results of that guess is by redoing the inventory and see how it was affected. And if it is balanced, that's great. If it's not balanced at that point, you keep going back and you repeat the steps as much as necessary until it is balanced. So in other words, the highly scientific method of balancing equations is to make an inventory and then guess, check your guess, and then keep on guessing. But there are some tips I want to show you. For instance, suppose we have a reaction like this, where we have a synthesis where we're going to take our elements and we're going to put them together to make a compound. Well, yes, you can create an inventory, so let's do that. So with an inventory, you're doing reactants and products. We have hydrogen, sulfur, and oxygen on each side of the equation. And I have 2 hydrogens on the reactant side, 8 sulfurs, 2 oxygens. And on the product side, I have 2 hydrogens, only 1 sulfur, and 4 oxygens. Now, my advice to students is when you have an element that has a lot of atoms, like this sulfur has 8, let's start with that. Let's make our first guess the balancing of sulfur. So I'm going to guess that I'm going to need to take this 1 and multiply it by 8. So I'm going to take this 8 and put it out in front of the compound that has sulfur in it. That's going to give me 8 sulfur atoms. Now I'm going to redo my inventory. I have 16 hydrogens, 8 times 2, and I have 32 oxygens on that side, 8 times 4. Not balanced. So now I'm going to go back and I'm going to balance the next highest one, which is the oxygen. So I'm going to multiply this by 16 on the reactant side. That'll give me 32. So I put a 16 out in front of oxygen. Now we're happy, 32 oxygens each. And then I can come back at the end here and balance my hydrogen by multiplying it by 8. So the mole ratio would be 8 to 1 to 16 to 8. Another trick. Suppose you have a reaction like this. And we're going to react that propane with oxygen. We're going to produce carbon dioxide and water. Alright, so we set up our inventory. Reactants, products. Carbon, hydrogen, oxygen on both sides. Reactants, 3 carbons, 8 hydrogens, 2 oxygens. On the product, 1 carbon, 2 hydrogens, and a total of 3 oxygens. We have 2 from the carbon dioxide and 1 from the water. Now, whenever you're dealing with an atom like that is split out between 2 different compounds, save that one to last. So we're going to do that one last. We're going to go ahead and balance our hydrogens. We're going to put a 4 on the product side in front of the water molecule that has hydrogen. And then we're going to go back and we're going to balance our carbons. So we're going to put a 3 out in front of carbon dioxide, 3 moles of carbon dioxide. And that takes care of our carbons and hydrogens. Now we can add up our oxygens. So oxygen is going to be, from carbon dioxide we have 6 oxygens, and from water we have 4 oxygens, so that's a total of 10. Now I can just go to my reactant side and multiply oxygen by 5, and that will give me 10 oxygens on each side. So again, if you have an element that's split out between 2 compounds on the same side of the equation, reactants or products, then you're going to balance that one last. Alright, another trick. Suppose you have this. Looks like almost the same thing. We do our inventory. Reactant side, product side, carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. 4, 10, and 2. And then 1, 2, and 3. Okay. So again, we're going to follow our technique. Let's take the hydrogens on the product side, multiply by 5. That will take care of my hydrogens. Let's multiply our carbons by 4. That will take care of the carbons. But now we have 8 plus 5, 13 oxygens. Alright, so what do we have to multiply by? We'd have to multiply by 6.5, or in other words, 13 halves. 13 halves times 2 will give us 13 oxygens on each side. Now, in thermal equations and something called a formation reaction in advanced chemistry, you're allowed to have fractions. At this level, no fractions. So how are we going to get rid of the fractions? Well, just like we would in math, we're going to multiply the denominator through. So I'm going to multiply everything in this equation by 2 and then rewrite it. So I'm going to have 2 moles of butane, and I'm going to have 13 moles of oxygen, 8 moles of carbon dioxide, 10 moles of water, and now everything's balanced. Last trick. If you have polyatomic groups on both sides, then I want you to put them as a polyatomic group in the inventory. Now this only works if they have the same group on both sides. So let's do something like this. Let's do make up that nonsense, and then we're going to do that, and that's going to produce this, and it's also going to produce, okay. So now we got to do our inventory, and there's a lot of oxygens here, and they're split out among multiple compounds. However, if you notice, we have a nitrate group on the reactant side. We also have a nitrate group in parentheses on the product side. We have a carbonate group on the reactant side. We have a carbonate group on the product side. So when I do my inventory, I'm going to treat them as groups. So I'm going to write sodium, I'm going to write nitrate, I'm going to write aluminum, I'm going to write carbonate, and I'm going to write them on both sides. Alright, so we have 1 sodium, 1 nitrate, 2 aluminums, and 3 carbonates on the reactant side. We have 1 aluminum, 3 nitrates, 2 sodiums, and 1 carbonate on the product side. So I'm going to go ahead and I'm going to start with the carbonate. Could have started with the nitrate, but I know from doing this type of problem that the carbonate's actually going to be easier. So I'm going to take the carbonate and multiply it by 3 on the product side, which means I'm putting a 3 out in front of sodium carbonate. That balances my carbonates, but gives me 6 sodiums. So now I'm going to go back and I'm going to put a 6 in front of sodium nitrate, because that will balance my sodiums. So that gives me 6 sodiums on the reactant side, and now it gives me 6 nitrates. Lastly, I'm going to put a 2 in front of aluminum nitrate, because not only will that balance my aluminums by giving me 2 on each side, but now I have 6 nitrate groups on the product side. So there's my balanced equation. 6:1 to 2:3 mole ratio. So again, this isn't difficult to do as long as you practice it. There are a couple of tricks, but that's really all.